1, 2, 3, 4, 5, 6. I'm going to be online soon. Going to be online. All right. We're online. Hello, everybody. Hello. The deal here is that it's getting ready for the midterm. Last online office hours before the midterm. I got a few questions. One person wanted to see a few, but then I don't know. So I just chose a random bunch of questions out of the book. Lots of 3-star questions, because why not? I'll do some 3-star questions for you, just so you can see what they're like, and some regular ones. I don't know. Where's my calculator? There it is. Okay. So let's go. The first question involved some of the derivations, reviewing some of the derivations from the list of possible derivations. So the first derivation is gravitational potential energy. We did this derivation in class, and here's how it goes. There's a rock. It's got some velocity. Then it goes up here, and it's got another velocity, v final. Okay? Here's the Earth. Here's the system. Earth, and then ball, the rock. Okay? And then the question is, what types of energy are there? There's kinetic energy, and there's gravitational potential energy. And this system here is closed, as in energy can't get in or out. So KE initial plus GPE initial is equal to KE final plus GPE final. And the purpose of this derivation is to come up with an equation describing the amount of gravitational potential energy as a function of how high off the ground it is. So say, I don't know, this distance h, whatever. So the trick to this is to look at the kinetic energy of the system. And the deal here is that we know exactly how much the kinetic energy changes. We know how the speed changes, right? X is equal to x initial. Why don't I write it in terms of y? Black. Y is equal to y initial plus v naught t plus minus g over 2t squared, right? And then v is equal to v naught minus gt. These are the equations of a motion of an object in free fall. And so we don't know a bunch of things about this, but we do know is their initial and final heights. So we know y initial, and we know y final. We also know the initial speed. We know that guy. So that guy, that guy, that guy. We don't know how much time it takes for them to go between there, but if you want to, we can solve for t in this case. V minus v naught over minus g. And then substitute y minus y initial is equal to v naught, v minus v naught over minus g over 2, v minus v naught over minus g all squared. So y final minus y initial is equal to v naught v final minus v naught squared over g minus g, I guess, minus 1/2 g v squared minus 2v v naught, I guess v final, plus v naught squared. And then we square this one, 2, 2. And what you get in the end is, alright, just keep going. Stop. I don't know, I'm sick. I can't. What's that? Okay, so you add them together. And if you add them together, I'm going to keep this minus 2g down here. If you add them together, you get v final squared minus v initial squared is equal to 2g, which, if you want to rearrange it, gives you minus 2g y final minus y initial is equal to v final squared minus v naught squared. Okay, so here's where the fun comes in. What you do is you divide both sides by 1/2. Oh, incidentally, if you want to, you can just start with this equation. I mean, that's an equation we know pretty well. So you divide that by 2, and then you multiply by m, the mass of the ball. And what you get is, this is the kinetic energy final minus kinetic energy initial. And according to this thing being closed, this should be equal to the kinetic, hold on, gravitational potential energy minus GPE final minus GPE initial minus mg y final minus y initial. Okay. And the result is you get that's a plus. All right. So the result is, I'm pretty messed up today. This becomes mg delta y, change in height, is equal to minus the change in the gravitational potential energy, or mg delta y is equal to the change in the gravitational potential energy. And that essentially defines what the gravitational potential energy is. So all you have to do in the next spot is decide where GP is equal to 0, and then measure the height from this point as your y variable. So put the origin here, and then you end up with, if at y is equal to 0, GPE is equal to 0, then at y is equal to y0 plus delta y. So mgy, that's equal to GPE plus delta GPE is equal to GPE. Wait, hold on. Oh man, I'm all gronked up. Anyway, long story short, what am I doing? I'm trying to say the gravitational potential energy is 0. The algebraic consequence is that the gravitational potential energy at height y is mgy. Hooray! The derivation looks like that. The second, alright, let's see if anybody's asking any questions. Nobody's asking questions. I'm going to drink some water. It'll make me less dizzy. I'm gonna eat a cough drop. Maybe it'll make me less dizzy. I probably should have gotten a 5-hour energy drink or something. I'm kind of fading fast here. All right. The next question was, there was a derivation that says something like conservation of momentum means if two isolated objects collide, their respective accelerations are proportional. So where would that come from? The idea is that between any two times, the change in momentum of one is equal to minus the change in momentum of the other one, because that means that the total momentum is conserved. So this is PA final minus PA initial, and this is minus PB final minus PB initial. And I can divide this by any number on both sides as I want, including T final minus T initial, including T final minus T initial, as that's just a number. And then I can take the limit of both sides. Limit as T final goes to T initial. This goes PA final minus PA initial divided by T final minus T initial. Limit T final goes to T initial. PB final, there's a minus sign here. T final minus T initial. And if you don't recognize it, this is derivative, time derivative. PA is equal to d by dt PB. And this corresponds to, the object's mass can't change, MVA. The object's mass can't change, but their velocities can. So this becomes MA d by dt VA. And wait, there's a minus sign here, I forgot. dVB by dt, and so this is MA A is equal to minus MB AB. So if you want to, you can say, hey, look, B over MA. They're proportional with respect to their inertias. That's fun, right? Let's see if anybody thinks that's fun. Hey, Coach, I was wondering ahead of time if for when you do questions, you could also state the equation you're using and the reason why. That would help a bunch. As in for textbook questions later on. As in for textbook questions later on. Oh, yeah, okay, I'll try my best. Derek David. All right. Well, these are the derivations, as far as I can tell. We've gone through them in class, so, look in your class notes. I'm going to drink some water. Going to see if somebody has anything to say on the chat before we move on. Nobody has anything to say. All right. So I thought we'd do some various questions here. There's a bunch of fun ones we can do. Lots of fun questions. So I was like, let's just do questions. Page 120. Question 50. Alright, let's read this out. Potential energy near Earth's surface. A 70-kilogram woman walks to the top of the Empire State Building, 380 meters above street level. What is the change in the gravitational potential energy of the system comprising of the woman and the Earth? use 70 kilograms. All right. We want to know the change in the gravitational potential energy. So that's going to be mg delta y. That's the formula I'm using. 70 times 9.81 times, how's the y changed? Y initial was 0. Y final is 380. Alright. Oh man, I can't imagine listening to me sniffle on the microphone. Really? The answer I get is 260,946 joules. 380 times 70 times 9.81. Yep. That's a lot of gravitational potential energy. Takes a lot of effort to get to the top of the Empire State Building. Next question, 52. An office worker has his lunch on the 53rd floor of an office building. In which case is the gravitational potential of the Earth lunch system greatest? The worker carried the lunch up from the 53rd floor in the elevator. He carried it up the stairs to the 53rd floor, or he got a ride in a helicopter to the top of the 68th floor building and then carried down the lunch in the elevator. Alright, so this is kind of the same question, only involves a sandwich. So here's our sandwich. It's a good sandwich. Yeah, pretty good. Here's our office building. And here's this special floor. Lunchtime. So the question involves routes. Woo! Alright, hold on. I gotta draw the sandwich on the floor. Alright, there's the sandwich. That's the sandwich's final position. Okay. And the question is, which takes more, in which one is the gravitational potential energy the largest? The change if you take it in an elevator, or the one if you go up the stairway, or the one if you go to the roof and then, I don't know, take the stairs and then the elevator down like that. And the answer is really fun. It has to do with configuration. Okay. Gravitational potential energy is a type of energy that depends on the configuration. Specifically, the height of the sandwich. Okay? So the gravitational potential energy is going to change if you change the height. But because of that, and as part of it, the deal is that all we care about is how the configuration has changed between the initial position and the final position. What doesn't matter is the route taken. So in this route, it takes the same amount of change. I mean, the position of the sandwich changes just in exactly the same way as if it did in this route. Okay. In this route, the gravitational potential energy increases, but then it decreases back to whatever. And so they're all the same. Does that make sense? Depends on the configuration and not the route taken to that configuration, which is interesting and fun. All right, next question, 58. What does that question look like? Two blocks are hung by a string draped over a pulley. Here, hold on a second. All right, back at it. Two blocks are hung by a string draped over a pulley. A 1 kilogram block on the left and a 3 kilogram block on the right. The two blocks start off at rest at the same height. What's the change of gravitational potential energy of the system blocks when the 3 kilogram block is dropped by 5.3 meters. What's the change in the kinetic energy of the system between release and this instant? And what's the velocity of the block at this instant? Hey man, that's pretty fun. This question's really fun. Should ask this on the midterm. Alright, here's your pulley. Boop. Here's your, alright, so there's a 5 kilogram and a 3 kilogram. Oh, it's a 1 kilogram? 1 kilogram. So that's how they are initially. And then they move. So this one has gone down a certain height. That height is 0.53 meters. Okay, so I should write that 5 a little bit better. So we want to calculate the change in the gravitational potential energy of the system. The deal here is there's two aspects to the gravitational potential energy. There's the change of the red block, which is m, which is 3, g, 9.81, times the change in height, minus 0.53. The gravitational potential energy is decreased that much. But the gravitational potential energy of the other block, this purple one, must have increased by 0.53. So the gravitational potential energy here is 1 times 9.81 times 0.53 plus. So you calculate this out. Minus 10.4 joules. Okay. So what formula is this? M1 G delta Y1 plus M2 G delta Y2. Does that make sense? Okay, so this is a closed system. I mean, rather, if the system is first block, block 3, and the Earth together. Okay, so that means that if the kinetic energy's gone down by that much, the gravitational potential energy has increased by that much. So that's the change in kinetic energy. Okay. So the, wait, no, hold on. KE initial is 0 because the blocks aren't at rest. So KE final is equal to 10.4 joules. And we want to know the block's velocity. So there's two blocks and there's two velocities. But here's the thing. They gotta go at the same speed. Because the speed this one's going up has to match the speed that this one's going down. Does that make sense? Should we expect questions with multiple pulley systems? No, not multiple ones. Have we did this? Is that after the cutoff? I can't remember what the cutoff was. Cutoff was springs, right? So we did springs and then multiple objects interacting. So we probably won't have any pulley questions on it. I just like pulley questions. They're on the final though, so pay attention. All right, for all those who are listening, Jessica asked, should we expect questions with multiple pulley systems on them? General answer is no. Right, so the velocity of this one is in the plus direction. The velocity of this one is in the minus direction. So because of that, we can actually solve for this. It's 1/2 the mass of the first one times the velocity, speed of the first one, plus 1/2 times the mass of the second one times the same speed. So this one's plus and this one's minus, but the signs go away when you square it. So you combine them, and this becomes 2v squared is 10.4. So v is equal to 10.4 divided by 2 square root, answer 2.28 meters per second, and it's in the plus direction. There's our final answer. Questions? Hey, look, 7 people are watching. Thank you for joining us, 7 people. What's the next one? What was that, 58? 58. Time for 63. It's a 3-ball question. 2 blocks are connected by a string draped over a pulley. The smaller block has half the inertia of the larger block. For which configuration, A or B in 1.7, are the speeds of the blocks greatest after the large block has descended a distance d? Ignore friction between the table and the sliding block and check your answer with a computation. Oh, fun. What a fun question. I'll call this configuration A, and I'll call this configuration B. Here's what's in the textbook. This one has a little block and a big block. And this one has a little block and a big block. And the question is, these 2 blocks are going to slide some distance d down same distance in both cases. Which one moving faster, A or B? Does that mean there will be spring question? Okay, hold on. David's asking a question. Does that mean there will be a spring question? If so, may I ask that you would solve one? No, the spring question was before the cutoff. So that everything after and including springs. Okay. I think there are spring questions in this particular problem set I've assigned myself, though. So you'll see me do some spring questions. But, no, not for a while. Spring's still a ways away. We've only just had our first snowfall. All right, how do you do this question? This question's really fun. Okay, so how do we talk about moving faster? We're talking about energy, right? So there's gravitational potential energy turning into kinetic energy. And there's gravitational potential energy turning into kinetic energy. Okay, in both cases. So how can we use this to figure out which one's going faster? Oh, I love this question. Maybe I should poach questions for the final out of the book. It just gets right to the heart of it. The deal here, though, is that there's 2 elements to this gravitational potential energy. There's the change in GPa of the first mass, and there's the change in the GPa of the second mass. In this case, there's only the first mass's height doesn't change, so its gravitational potential energy doesn't change at all. Okay. So let's multiply by the minus sign. Okay. Hold on. Oh, I've got another question here. It says, also, Jessica's asking, and I have the same question, whether we should expect multiple pulley systems on the exam. Thanks. No! I answered it. When did Jessica ask it? 10 minutes ago. Keep up, Jean-Philippe. Hey, Prof. Another person goes, hey, Prof, what's the probability that there will be forces in elevator questions? I can't tell you the probability, but I can tell you that I really like forces in elevator questions. So, I don't know. I can't rightly tell you. But there's probably going to be a forces in elevators question before the final exam. Or rather, if not here, then in the final exam. Because I really like them. So, that's it. It's important. It's important because the normal force in an elevator isn't the same as mg. Everybody's going to say that the normal force is mg, and it's not. It's never the same as mg, especially not in an elevator. All right. Jean-Philippe just said they're sorry. Don't worry about it, Jean-Philippe. You're a good person. All right, let's get back to it. So which one's bigger? I'm setting the question up in this way because I want to point something out here. The kinetic energy is, of course, distributed through both of the objects. But here's the fun thing. See this one? It's going to be the same number as it is over here, because this second mass is moving the same distance, right? So this term is going to be the same, and it's going to be a negative number, right? So this negative number, this overall positive number, means that the gravitational potential energy is going to increase. You dig? Okay. So how do we compare these two? For one thing, you can be like, well, how do we know about speed motion? In the previous question here, I argued that the speeds, their velocities are different, of course, but the speeds have to be the same to keep the rope from extending. And that's certainly the case here. So in other words, how big the GPE is kind of is described by how fast the system's moving. Okay. So what's the distinction between these two sides? That one number is the same as this number. So what? I want to compare this number and this number. The difference is this. In this case, the gravitational potential energy of that term is increasing. Okay? Gravitational potential energy of that term is increasing. And so this whole thing is going to be a negative number. So this is a positive number. This is a negative number. And so when you put them together, you get a smaller number than if I hadn't subtracted that thing. In other words, because these are the same and because this is because the gravitational potential energy is positive, or rather the change in gravitational potential energy of this term is positive, so this is, oh geez, I can't even see it. This term overall is going to be negative. This kinetic energy is smaller than this kinetic energy, so we know that the objects are moving slower. You dig that? That's fun. Man, I'd do first year physics questions all day if I could. That's 63. All right. I mean, I did a lot of these questions back a couple weeks ago. If you want to see more of these questions from Chapter 7, you can pull up your thing. In fact, I did a lot of questions from Chapter 8 last week as well. So, more friction questions too last week. I did a lot of questions from the book already. All right, Chapter 8, page 140. No, not 140. No, not that one. 136. Okay, hold on. Derek David just asked a question. Derek David said, just on clarification, for conservation of momentum, do you use Ke initial plus E internal equals Ke... Oh, okay, hold on. I gotta answer Derek David's question before I start another one. Okay, Derek David. I'm gonna read the words out explicitly. People in live chat can read it, but I don't think the system saves live chat questions. So Derek said, just on clarification, for conservation of momentum, do we use Ke initial plus E internal is equal to Ke final plus E internal, or do we use Ke initial plus potential energy initial is equal to Ke final plus potential energy final? Okay, the answer to this depends on the question. So first off, these aren't conservation of momentum questions. These are conservation of energy questions, and I'm going to assume that that is just a Freudian slip because it's easy to say the wrong word or type it into the internet. So these are conservation of energy questions, not conservation of momentums. I'm going to presume you know that. Okay, so which one do we use? This is a fun thing. Let me draw a Venn diagram. Venn diagram. Here is all the different types of energy. Some energy is kinetic. Some energy is internal energy. This guy, internal energy. Okay? So it's always the case that this is true in a closed system. You dig? It's always the case that it's true in a closed system. So one question I might ask you is, how has the internal energy changed? And you know, that might be fun. Then you look at the initial kinetic energy and the final kinetic energy and subtract them, and that tells you the change in the energy. That said, there is a type of internal energy called potential energy. Potential energy has the ability to turn back into kinetic energy. So, this equation is super useful when we're talking about before and after questions. Because in this case, all of this equal all of this is really useful because often we have a way of calculating how much potential energy there is initially and how much potential energy there is at the end. Like in gravitational potential energy questions. So in gravitational potential energy questions, we know how much potential energy there is at the start, we know how much there is at the end, and that will inform, that plus conservation of energy will inform how the kinetic energy has changed, and thus how the speed and velocity has changed. But, so you might ask, which question is more useful? Shouldn't we always just assume that the answer is this type? And the answer is no, you shouldn't assume that. Because there's more than one type of internal energy here. The types aren't redundant. There's another type here we can call heat or waste energy. Speak of the devil, I'm freezing in my office. All right. So, in other words, there are some systems where the kinetic energy can turn to potential energy or it can turn into waste heat. And in that case, this top equation is the more useful of the two But I can still rewrite this in a more useful way for answering questions. If I want, and I'm in a system where there's more than one type of internal energy, you can rewrite this equation Ke initial plus heat or waste energy plus potential energy is equal to Ke final plus heat final plus U final. Okay? U is the standard way to write potential energy. I've been doing it all the time. So in this case, the kinetic energies you can calculate or are given to you. The amount of, or the potential energy is something you can calculate or is given to you. And so you can use the conservation of energy to figure out how much heat has been generated. There's even more complicated versions of this because there's like another type of internal energy you can call like I think the book calls it source energy. It's like, you know, for example, like chemical potential energy. Or, you know, you got a battery, whatever. So in this case, you would rewrite this as kinetic energy initial plus source energy initial plus heat initial plus potential energy initial is equal to Ke final plus source energy final plus heat final plus U final. So how would you use this? You know, you could be asked a question, say like, hey, a car goes up a hill and the car burns 30 joules worth of gasoline. So that tells you about source energy. And the car goes, it has a certain amount of mass and it goes 70 meters up the hill. So that would tell you about the potential energy. If the car starts moving at 3 meters per second and ends up moving at 16 meters per second, figure out how much waste heat is generated. Okay? So the question you're going to use to solve an energy problem kind of depends on the sophistication of the problem, what different types of internal energy there are. Generally speaking, this equation is always correct, though not always useful. These forms of the equations are more useful when you break up the internal energy into different types. Potential energy can always turn back into kinetic energy. There's kinetic energy. Source energy generally can't be reclaimed once it's been turned into kinetic energy. And then heat. Does that answer your question? I hope it does. All right. Did I do question 5? Question 5. Question 5 goes like this. This is on page 136. If a single known force is exerted on an object for a certain time interval, you know the change in the object's momentum. However, you don't know its change in kinetic energy. Why not? This is a fun question. Let's do I'll do an example called pillow pushing. Where you're standing here, minding your own business, and somebody throws a pillow at you. What do? You take your big old boxing glove fist and you hit it. So you apply a force to it for a certain amount of time. You can draw a force versus time graph if you want. Look, you're giving it lots of force. The area under this graph tells you the object's change in momentum, right? And so you can use it to figure out what the final momentum is of the pillow. Okay. What about the kinetic energy? Okay, so wait, hold on. This is P final. Go P initial. All right. What about the energy? And the answer is really fun. The answer is that there's more than one type of energy in the pillow. There's kinetic energy, and certainly this has changed, right? Well, not necessarily. Maybe you bopped it out at the same speed it was coming in on. So in that case, the kinetic energy might not change at all. But furthermore, you've changed the shape of the pillow. First, the pillow was a nice rectangle, and after bopping it, it's kind of shaped like a... It's no good. So you can try this at home. Go home, punch a pillow. Punch a pillow at your parent. Don't do that. Don't abuse anybody because I told you to. I'm just alliterating here. Change shape. Generally speaking, when things change shape, their internal energy is changed. So in other words, not all of the energy is going to manifest as kinetic energy. So even if you know, I mean, yeah, long story short, we don't know how the kinetic energy changes because energy is more complicated than momentum. There's no such thing as internal momentum. There's no such thing as potential momentum, but there are of energy. And so even if we know all about how the momentum is changed, that doesn't necessarily tell you anything about how the energy has changed. The internal energy might have increased by a lot, or the kinetic energy might have increased. Even if you say something like, hey, when I punched it, I gave the system 3 joules of energy. Did that all go into kinetic energy? How much of that went into changing its shape? We don't know. All right, next question. Number 23. I tried not to just choose the 3-ball questions, but I really like doing the 3-ball questions while I'm on the internet because they're fun. And also, you know, I don't know the answer. I have to think out the answer on my feet. And so you get to listen to me problem solve. If there's any other questions, ask the question. Right now I'm just doing online random questions from the book. So, okay. I just got another question. For the energy things, E internal is just the change in the kinetic energy. E internal is just the change in kinetic energy. Kind of. They're kind of different. It's kind of more complicated than that. Okay. So, Derek just asked regarding his question here, hey, is internal energy just defined by delta E internal is equal to negative delta KE? Is this all we're talking about? So it's definitely not interchangeable. The idea is definitely not interchangeable with the potential energy. Internal energy is not equal to potential energy. They're different concepts. I think what internal energy is it's a bunch of things. It's, how should we put it? There's 4 different types of energy. Internal energy is in part a recognition that there is some energy that's associated with configuration. Okay? So we can recognize that, you know, changing the shape of something requires energy. Sometimes that energy can be restored. So in other words, sometimes that energy is stored in the system. Like if you squish a spring, that energy is stored inside the spring, and then you can release the energy later. Sometimes that energy isn't stored in the system. It just goes into changing the system, and then you're done. Like with a pane of glass. You smash a pane of glass, you're done. Roughly speaking, there are 4 different types of energy associated with whether they're related to configuration. Wait, hold on. Whether they're related to configuration or whether they're related to motion. All objects on Earth have some configuration energy associated with them, from the rocks to the trees. It took energy to put those objects in those particular configurations, and it would take energy to change them, or changing their configuration might release energy. Okay. But in essence, the idea here is that there's 2 different types of energy: motion and configuration. But you add to this the concept that sometimes you can get the energy back, sometimes the energy is macroscopic, and sometimes it's microscopic. What was the concept? We talked about this in class. It's called coherent and incoherent. Coherent and incoherent. So coherent kinetic energy is what we usually call kinetic energy, or macroscopic kinetic energy, right? It's large objects that are moving. There's incoherent motional energy, though. It's like vibrations of atoms, or vibrations of, a whole bunch of gas molecules that are bouncing around. We call this heat. So heat's a type of kinetic energy. Well, it's a type of motional energy, but it's not a type of kinetic energy that I can track in any kind of way. Because in order to do so, I need to know what the speed and mass of every single mote of atom in a room, right? So there's moles and moles of atoms. I can't track all that. So in essence, like, I don't know how to track how much kinetic energy there is in heat. It's something I can measure with a thermometer, because I know how heat behaves, but it's not something I can calculate outright. It's not macroscopic. Configuration energies, same thing. There's coherent configuration energy, which we call potential energy. And incoherent configuration energy, which is usually, broken crap. Broken stuff. But also waves. What's my point? My point is that these types of energy here are all called internal energy, because they can't be easily calculated just knowing about how everything's moving. It's made of really distinct things, right? Like this one here is like a spring being squished. This one here is like a window being shattered. In other words, at the microscopic level, if you're just dealing with 1 or 2 atoms or 1 or 2 molecules, everything looks like coherent. But in our larger macroscopic world, we have to admit that, like, okay, some changes in configuration, it's just not coming back. You break a window, that's different than if you tear a molecule apart, you can always put it back together and get the energy back out. But if you break a window, you can't unbreak the window and get the energy you put in back out. So, long story short, potential energy is a different concept. Potential energy is a different concept than internal energy. Internal energy kind of has to do with this whole big construction. Potential energy is just a part of it. It's a useful thing, though. In systems with potential energy, we usually have an equation describing exactly how much potential energy there is. And so you can look at the configuration of things and judge based on their configurations, like a spring, right? If I know what the spring constant is, and I know how much it's been squished, I have an equation describing how much potential energy there is in the squished spring. Okay, now David he asks, how would we calculate said internal energy if we were asked a question like that on the midterm? Okay, so here's the thing about internal energy. Everything's got a lot of it. Technically speaking, all of the atoms in your body have a significant amount of internal energy in them. We can't account for all the internal energy in it. We can't account, when you're talking about internal energy, you're usually not referring to like, hey, if I changed all my hydrogen atoms to helium atoms, how much energy would I get? So on questions like you might get on the midterm, you'd figure out the changes in internal energy. We'd ask you how the internal energy has changed. Or we'd ask you maybe how some aspect of the internal energy has changed. I don't know how much energy is in heat in the room at this moment, but if you do the calculation, you can figure out how much heat was added through some interaction. Okay? So usually in these questions, when we're talking about internal energy, the focus will be on asking questions about the changes in internal energy rather than asking you about what the internal energy is at the start. Does that answer your question, Derek? All right. Better. Got to get back to my homework here. 23. All right, where are we? 23. You are carrying a 3-year-old niece on my shoulders. Oh, she's 5 now, though. In an elevator cabin that's moving upwards at a velocity of 1.5 meters per second and a constant downward acceleration of 1.0 meters per second squared. My inertia is 50 kilograms. Oh, I wish. And my niece's inertia is 20 kilograms. And the cabin's inertia is 100 kilograms. Not much of a cabin. Free body diagrams for the elevator cabin, your niece, and yourself. Labeling forces and using notations introduced in principles. Make sure the lengths of the force vectors are appropriate to the magnitude of the forces. Okay, yeah, this is fun. Got to draw a picture so you know what I'm talking about. This is me. This is my niece. This is the elevator. Okay. So, we want 3 different, the thing's asking us for 3 different free body diagrams. For the cabin, my niece, me, and the niece. So, each of us feel gravity. We'll start with that. Cabin feels a lot of gravity. I feel a moderate amount of gravity. Whoa! And my niece doesn't feel very much gravity at all. Okay, maybe I should have drawn these longer, just a little bit longer, for what's to come. Where you go? What? What? Hey, behave. And then this one, a medium one. FG. Okay, so now they're all different sizes. At some point, could I please do a Galilean relativity question? Thanks. Tell you what, Derek David. Find me a Galilean relativity question that you want me to do, and then write it in the thingy, and I'll do it last. Okay. If you find me a question from the textbook, I'll do it. Like the black textbook, look up the number. Okay, so let's start with my niece. What's touching my niece? Only me. So there's a force upwards from me. Wait, hold on. Is it bigger or smaller than the force of gravity on my niece? It's saying we're accelerating downwards. So the net force on my niece must be downwards pointing. Ah, geez. Sorry about that. And so the force from the ground, force from me, and niece, has to be pointing up. But it's only a little bit. Now, that means that there's a pair of interactions. Because I'm pushing my niece upwards, I must be feeling a force downwards. Same length. Okay. So what else is touching me? The ground is touching me. So there has got to be a force pushing me upwards from the ground. F me cabin. It's bigger than the one from my niece, but I want the total force pointing down. You dig that? So this force, the blue one, can't be bigger than the red and the black one combined. Next part. The cabin is touching me, and that means the cabin feels a force pushing downwards, equal in length. F me cabin, and then the cabin also feels a tension force pointing up. Let's get this right length. It needs to be big, but not big enough to cancel out me and the force of gravity. Okay? So that's about the size of the forces. Next part. Let's take the magnitudes of as many forces as possible. Identify the forces that form interaction pairs. I've identified them in colors. Briefly obtain how they got their magnitudes. Okay. Well, I can calculate some of these forces right off the bat. This black one, gravity on the cabin is going to be minus 98.1. No point there. 981 newtons downwards. Force on gravity is me is going to be minus 50 times 9.81. 490.5 newtons. And the force of gravity on my niece is going to be 20 times 9.81. 196 newtons. Okay. So, can I figure out how big the other forces are? I can, but I have to do an intermediate step. I have to talk about the acceleration of each of these. The acceleration of the cabin is minus 1 meter per second squared. The acceleration of me is minus 1 meters per second squared. And the acceleration of my niece is minus 1 meter per second squared. And that means the net force on the cabin is going to be m times a minus 100 newtons. This force on me is going to be minus 50 newtons. And F net on my niece is going to be minus 20 newtons. This in turn tells me what these forces are. This force plus this force have to equal, I guess these are minus, put minus signs in there. This force plus this force has to equal minus 20, so this force here is 196 minus 20. 176 newtons, pointing upwards. This force then points downwards, 176 newtons. Okay? Since that's 176 newtons pointing downwards, this one plus this one plus this one have to add together to get 50. So that's minus 490.5 minus 176 so this one has to be 61 6.5 newtons. Yep. Okay. And that means this one must be pointing down in the same amount. Okay. So this plus this have to add together, plus this one have to add together to be 100. So 981 plus 616.5 minus 100. So this one has to be 1497.5 newtons. And that's what all the forces are. Isn't that fun? That question's pretty good. Put that one on the final. Question 34. Equations of motion. You push with a steady force of 19 newtons on a 48 kilogram desk fitted with casters. Casters are little wheels. On its 4 feet. How long does it take to move the desk 5.9 meters across a warehouse floor? Presumably, starting from rest. Okay, so there's only one force on this, presumably, which is 19 newtons. And so F net is going to be plus 19 I hat. And then acceleration is going to be F net divided by the inertia. So it's going to be 0.4 meters per second squared. And so the equation of motion of this is going to be, constant acceleration question. X naught plus V naught t plus 1/2 AT squared. So we'll start at x equals 0. I want to know what time it reaches 5.9, starting from 0 velocity, 0.4 t squared. And now I solved this for t. T squared is equal to 5.9 times 2 divided by 0.4, 29.5. So t is equal to square root of that, 5.4 seconds. Okay. All right, I'm going to add David Derrick's question to the list. Page 98. Question 34. Okay. If anybody else has questions they'd like to see me do, add them to the list, please. All right, 34, 42. You were climbing a rope straight up towards the ceiling. Oh, yeah. Yeah, right. What magnitude and direction of the force must you exert on the rope to accelerate upwards at 1.5 meters per second squared, assuming your inertia is 60 kilograms? All right. This is a great question. Here's the rope. Here's me going up the rope. Got Lucio legs. Okay, so what's the magnitude and direction of the force you must exert on the rope in order to accelerate upwards at 1.5 meters per second squared, assuming my inertia is 60 kilograms? So before I do that, let's talk about my motion. I know the acceleration is, I'll call that the I hat direction. The acceleration is 1.5 I hat. So the net force is going to be that times 60. 90 newtons upward. Okay. But there are two forces acting on me. There's a force from the rope pushing up, It's not a tension force. It's kind of a tension force. It's like the friction force between my hands and the rope. And then gravity pointing down. So gravity pointing down is got to be 9.81 times 60 minus 588.6 I hat. And so F rope, we can calculate it as being this plus this equals that. 679 I hat. That's got to be the force pushing upwards from the rope. What's doing it? My hand's on the rope. Is it friction? Yeah, it's friction. Imagine trying to climb a rope that was really, really slippery. You couldn't do it. You'd slide down the rope. So it's static friction between your hands and the rope that's doing it. So this means that there's a force pair. The rope is pushing me upwards, so I push downwards on the rope. I push down with force 67.9 newtons. Hey, you want to know something fun? Here's a question. Does the rope need to be attached to the ceiling in order to climb it? What do you think? The answer's no. If I cut it from the ceiling... Oh no, the rope is cut. What'll happen is I can still push off the rope. If I push off the rope, I mean the rope's going to accelerate downwards. The center of mass of the rope is going to move downwards, but just under the force of gravity. I can also apply my own force to it, push it downwards, and thus keep on pushing up. Kind of Roadrunner style. You can keep climbing a rope after after it's been cut. It's just not for very long. So I can keep going as long until the end of the rope reaches me, and then after that I'm doomed. But you know, pretty hard to push that much on a rope. The nice thing about climbing a rope that's stuck to the ceiling is that the rope isn't moving relative to you. If it is, you have to move your hands really, really, really fast. And so that's why you fall off. Okay, but whatever. Don't worry about that. If the max tension the rope can support is 1,225 newtons, what's the maximum inertia the rope can support at this acceleration if the inertia of the rope is so small that the gravitational force exerted on the rope can be ignored? Right. So the deal is that if you hang a rope from the ceiling, it'll be under tension because the rope has to support its own weight. So what this question is assuming is that the rope has no mass, so it doesn't need to support its own weight. In other words, it's telling you to ignore the mass of the rope. So let's just write out this equation, this one here. F net is equal to 1.5 times the mass, and this is equal to the tension force plus the gravity force. So 1.5 times the mass, my mass, is the maximum tension plus minus 9.81 times my mass. And you solve this for m. .108 kilograms. Note that if a person was 108 kilograms, they could hang from the rope, just not climb it at this acceleration. In fact, they could climb it more slowly than this, but if they climbed it at this acceleration, the rope would break. All right, what was that, 42? 47. 47, what's that question? All blocks in figure 8.45 are identical, and you can ignore every friction in the pulleys. Rank the configuration in increasing order of tension in the rope. Note Use free body diagrams. Oh, that's fun. Oh man, what a fun question. You ready for this question? I'm going to draw it for those of you who don't have the books in front of them. Pulley. Post. It's like an ugly flower. Pulley. Post. I'll call this A, B, pulley, pulley, and pulley, pulley. Okay, so the first one is tied to the post, and it has 1 block worth of mass. The second question has 2 pulleys hanging like this, same amount of mass on both sides. The third one has this and then double the mass. The fourth one has 1 mass going like this, and then 2 masses here. I guess the thing likes calling this one B, C, D. Okay, so one question we might ask is it possible that the system is in equilibrium? Is it possible that the acceleration is 0? Yes, 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 no. Okay, so let's consider that one last. For the first one, the free body diagram looks like this, of the mass. Free body diagram looks like this. Tension pulls up, gravity pulls down. Second one, there's 2 masses. Each of those, mg, mg, tension, tension. So I'd wager that in the second one, it's in equilibrium as well. I'd say that the first one's in equilibrium and the second one's in equilibrium, which means that the tension in both these cases are the same. TA looks like it's equal to TB. C, gravity is extra strong, 2mg, right? Gravity is extra strong, so that means the tension force has to be extra strong as well. I'd wager that this one is in equilibrium too. Okay, somebody's just asked a question. Is my name Jeff? Hey Jeff. I have done the sample midterms and went through all the questions you solved. Is that enough practice for midterms, or should I do something else? Alright, here's the thing. I can't tell you when you're ready. Only you can tell yourself when you're ready. I can tell you, though, that if you stay up till 2 a.m., you probably won't do too well on the test. So eat a good meal, have a good sleep tonight. Aside from that, I don't know, what can I say? I'm not going to tell you you're ready. Did you do the tutorial questions? Did you look through the class notes and go through all the things we talked about in class? All the examples we did in class? I mean, there's always more practice you can do. Only you can tell yourself when you've done enough. I've spelled out in the sheet exactly what I want from you. You can use that as a checklist and go through the checklist and say, hey, I did all these questions. I know how to do all of them. I am a master. And then maybe you are. I don't know. There's such a thing as called over-preparing, but there's also a thing called, I'm not going to tell you you're ready until you've done the test and I see your grade. Okay? Sorry, I can't reassure you any other way. All right, so it looks like TC has got to be bigger than TB and TA. What about this third one? Let's draw free body diagrams for this. Okay, so this mg is going to be the same, and this one, mg, the second one, mg is going to be twice as long, 2mg. What about their tensions? Here's the thing. The tension here is going to pull this one up, and it's going to let these ones fall. But they won't fall as fast as they would in free fall. So the tension force here has to be bigger than mg, and it has to be the same size on this one. I'll call it TD, like the bank. So it's the same in both cases. And because we know that this one has to accelerate up and this one has to accelerate down, TD has to be bigger than mg, but it has to be smaller than 2mg. Does that make sense? So the long and the short of it is TC is bigger than TD is bigger than TB. That's fun, right? All right, what's question 60 look like? Oh, I skipped all the spring questions. We'll do them next week. All right, 47, 60. Why does a drop dinner plate break if it lands on a tile floor, but not when it lands on carpet? So here's the plate that I've dropped. It's moving at the same speed in both cases right before it hits the surface. Okay. Tile floor's right here. Carpet, well, the floor is here. Thing about carpet, it's long. Now, it is the plate's destiny to go from moving to not moving. Let me extend this out here. It's contact force, thing that slows it down. Normal force from the carpet, normal force from the thing, tiles. It's the destiny of this thing to not be moving. Okay. But here's the big distinction. In this case, the contact force starts applying over a long distance. Whereas the contact force in this case only starts applying once the plate touches it. The deal is that the carpet is longer, and so the contact force starts earlier. It's going to take the same amount of force. No, hold on. The change in momentum is going to be the same in both these cases, but in this case, the amount of time it takes is more time than on the tile floor. Delta P over delta tile. This is a small number. It's usually the average force. And that's going to be a big number. Whereas delta P over delta T carpet, this is going to be a medium-sized number. So the force is also going to be medium-sized. Does Babowski have a similar exam to... Okay, so a guy asks, does Babowski have a similar exam to as you or no? The answer is they're kind of similar. I mean, they cover similar stuff. Jake has a slightly different way of asking questions, and he's better than me at it. So also Jake Bobowski's class, the other section of physics, has an hour and a half long test period, whereas our test period is 50 minutes. They were pretty close in the first. Hold on, somebody just asked me something. Will you ever do this in a classroom on campus? What do you mean? Okay, let me go back to Bobowski's question. So Jake Bobowski's class has more time for the exam, but and Jake asks slightly different types of questions than I do. That said, I imagine that any of you should be able to go into Jake Bobowski's class and get about the same exam as his same score on average as his students do, and I expect that his students should be able to come in our class and get the same average score. So they're they're meant to be comparable in difficulty. So the long and the short of it is, I mean, we have a shared final exam, so the course contents are very similar. So does he have a similar exam? Yeah, he does. Okay. Next person asks a question. Will you ever do this in a classroom on campus? What's the question? 75 minutes? This e-tutorial? What are you talking about? All right. Fenosira, explain yourself. Give me more information. I still don't know what you're talking about. Do you mean like questions? Like I'm doing right now, where I do a whole bunch of random questions? Will I ever do this in a classroom on campus? I don't know. I'm going to drink water. Hold on. Please elaborate. Ah. 60. What's the next question? 68. All right. Back to it. So yeah, for this question here, the plate feels more force. The amount of momentum has to change by the same amount, but the force is applied over a much shorter time. And so it feels more force. Okay. So the person's clarified their question. Bobowski's midterm was 75 minutes long. Yes. This tutorial, will the medium ever be your voice in a classroom instead of through the computer? What? Hey, Kamal Narayana just asked, hey coach, could you go over the potential energy derivation? When we finish the online tutorial in about 15 minutes, I did it at the very start. So, if you come, well, you should continue watching, but after it finishes, maybe 5-10 minutes later, YouTube will have an archived version of our conversation, and you can go back and watch me do the derivation. Okay, so still trying to parse this one question. Will the medium ever be my voice in a classroom instead of through the computer? I mean, I teach you a class 3 times a week in person. This is just like example questions so that you can see some examples. I don't understand. Please continue elaborating. Like, what do you... Oh, I see. 75. Bobowski's midterm is 75 minutes long. Yeah, okay. So it's an hour and 20 minutes or an hour and 15 minutes instead of an hour and 20, because he needs to collect it. It's still more than our 50 minutes, though. Okay, so yes, I don't understand. Will the medium ever be my voice in a classroom instead of through the computer? Yes? That's such a strange question. I teach your class. I give you lectures. Ah! Okay. If you elaborate more, go ahead. I'm going to start the next question. Question 68. A 1.2 kilogram ball dropped from a height of 3 meters onto a steel plate rigidly attached to the ground, bounces back up to a height of 2.5 meters. What's the impulse delivered to the ball by the plate? And what's the coefficient of restitution? Okay, so I'm not going to do part B of that question because we haven't talked about coefficients of restitution. But the first part's fun. So, this is a great question. Essentially, we're asking about the change in momentum as the ball interacts with the plate. Okay? And to do that, I need to find the initial velocity right before it hits and the final velocity right after it hits. So to figure that out, what I'm going to do is I'm going to use the gravitational potential energy. So I know the initial height is 3 meters. This is 1.2 kilograms. And then the final height here is 2.5 meters and 1.2 kilograms. So, going to split this whole thing down the middle. Conservation of energy both times. Is energy conserved during the collision? No, it's not. The speed after the collision isn't the same as the speed before. It would bounce to the same original height. So, I'm not going to use conservation of energy throughout, but I'll do it at the start. Kinetic energy plus potential energy. Kinetic energy plus potential energy. So initially when the ball's this high, the kinetic energy is 0. They don't tell us this outrightly. It's implicit in the description. And the potential energy is mgh. So it's going to be 1.2 times 9.81 times 3. Then, when it's at the bottom of the bounce, the kinetic energy is 1/2 times the mass times v squared. I don't know what v is, but I do know that the potential energy at the bottom is 0. Okay? So I can use this to figure out what the final speed is, or the speed is at the bottom. 1.2 times 9.81 times 3 times 2 divided by 1.2 square root. Answer 7.67 meters per second. And then afterwards, I don't know what the kinetic energy is initially. So it's 1/2 1.2 times v squared. I don't know what v is. Plus, I know the kinetic energy is 0. Or the potential energy at the bottom is 0. At the top of the arc, the kinetic energy is 0, and the potential energy is m times g. No. 9.81 times the height, 2.5. So I can solve this for v. 1.2 times 9.81 times 2.5 times 2 divided by 1.2 square root. Answer 7.00 meters per second. All right. Now I'm going to compare just these two. The initial momentum is going to be, let's see, I'll call I hat that direction. The initial momentum vector is the mass, 1.2, times the velocity, minus 7.67. The final momentum is the mass times the final velocity, plus 7.00. So the initial momentum is 7.67 times 1.2 minus 9.2 kilogram meters per second. And P final is 7 times 1.2, 8.4 kilogram meters per second. Delta P is P final minus P initial. So that's plus Hey, you know what? I'm going to add the I hat here because there's something fun. I hat. Okay. So it's going to be plus 17.6 kilogram meters per second in the I hat direction. And this is the direction of the force. You divide that by the amount of time it took, and that's the force. All right, so that's the impulse. Good work. Don't be impulsive. All right, so which one is that? 68. Now 70, I guess. Oh yeah, it's a three ball problem. I win. Oh, gross. All right. Trigger warning. This one involves car accidents and people getting in car accidents. So if you're triggered by that kind of stuff, you can hop ahead. That said, if you're not, car safety is important, and there are simple physical reasons why you shouldn't do things like hold a baby in your lap instead of putting it in a car seat, or drive without a seatbelt, or drive too fast, or drive. There's a whole bunch of real physicsy reasons why car crashes hurt in the particular way they do, and this is actually a pretty good opportunity to explore them. When it crashes into a bridge support that does not move, a car goes from 80 kilometers an hour to 0 in 1.23 meters. What's the impulse delivered to the 70 kilogram driver by the seatbelt, assuming the belt makes the driver's motions identical to the car's motions? So what we're saying is, you got your car driver, and initially they're going 80 kilometers an hour. And then a distance 1.23 meters away, they come to a rest. Okay, so we want to know what the so what's applying a force to you? Which way are you accelerating? Essentially, you're accelerating that way. So what's applying to the force to you? In this case, if you're lucky, it's your seatbelt. Hello. Part of the reason you have to wear a shoulder strap is that it keeps you from flopping around. And also, there's more parts of the car pushing on your body, so you flop around less. 80 kilometers an hour is equal to, let's convert this into meters per second. How do you do that? With a little chain thing. All right, so first let's go from kilometers to meters. There's 1,000 meters in 1 kilometer, so that's the conversion there. Let's convert hours to minutes. 60 minutes in 1 hour, and I want it in seconds. So that's 1. Okay, do the multiplication. 1,000 divided by 60, 22.2 meters per second. So your initial momentum is 70 kilograms times 22.2. 1555.6 kilogram meters per second. All right, P final, 0. So delta P is minus 1555.6 kilogram meters per second. Okay. What's the average force exerted by the belt on the driver? Well, to figure out the force, I need to find delta T. And to find delta T, I need kind of A. Yeah. So we can do that, though. For instance, 2A delta X is equal to V final squared minus V initial squared. So 2A, I don't know what A is. Is there any way to find this without that? I know what delta x is. Yeah, whatever, I'll do it the long way. So this is 1.23. The final velocity is 0. The initial velocity is 22.2 squared. 22.2 all squared divided by 2 times 1.23 minus 200 meters per second squared. So if I want, I can go 0 is equal to 22.2 minus 200 times t. This is v final is equal to v initial minus at plus at. 22.2 divided by 200. T is equal to 0.111 seconds. Oh, that's very fast. So delta P over delta T is equal to 1555.6 divided by my answer minus 14014 newtons. Incidentally, maybe we could calculate using MA instead. Minus 200 times 70, right? Yeah. 200 times 70, that's minus 14000 newtons. Yeah, it's the same. You might be like, hey, what's with these numbers? Those are sig figs. Don't worry about those. Same number. Okay, so what's the average force exerted by the belt? That's the average force exerted by the belt. If the driver were not wearing a seatbelt and flew forward until he hit the steering wheel, he would be stopped. So C. What if delta T instead was 0.0145 seconds? Okay, by the steering wheel on your noggin. Compared to this. That's fast, but it's 10 times slower than this. Delta P over delta T gives you so this is 1555.6 divided by 0.0145. This is 1.07 E6 newtons. This is 10 to the 4. This is 10 to the it's 10 to the 6. It's 100 times more force. All right, Kamal's got a question. Question: if two people are in an inertial reference frame, will they agree on the total momentum and total kinetic energy? I'm going to answer Kamal's question now. Wait, no, I'm going to finish this question halfway through, and then I'll answer Kamal's. Okay, so would he be likely to survive the crash described in part C? Justify your answer by comparing the force of the steering wheel driver to the gravitational force exerted on him. Okay, so one way people talk about forces is in terms of multiples of the gravity force. Okay, so this person feels a certain amount of gravity force, which is 9.81 times 70. They feel 686 newtons worth of gravity force. The amount of force they feel from the car accident, 1.07 E6 divided by 686. The amount of force from the accident is equal to 1,560 times his gravity mass. Answer's no. I mean, maybe. Things happen. Like, there was once a time when, like, the reason you would die in a car accident is you would go through the windshield, and that was before, like, special glass that shattered, and so the windshield would cut you up and you'd bleed to death. And then there's another time when, yeah, so essentially seatbelts there slow down your motion. People still whiplash into the steering wheel, though. So they installed airbags, which further increase the amount of time you're feeling an acceleration and spread out the force so that all the force isn't given to you by the pressure of the seatbelt. So your overall body feels, you know, the same impulse, but it's spread out over a longer time, and the airbag lets it spread out over more of your body, and so you're more likely to survive. Kamal's question. If two people are in an inertial reference frame, what did I write? Inertial reference frame, will they agree on P total and KE total? So that's the question Kamal asked. It's a good question and one liable to come up on the midterm. So, two people are in the same? All right. So, inertial reference frames are ones where stuff doesn't roll around for no reason. So here are two people. Here's two more people. Okay. VA. If they have the same stuff's bouncing into each other. Okay. So So, in the first case here, I've drawn two people in the same reference frame. That means they're traveling at the same velocity relative to the ground. So, they have the same velocity. Oh, that's what I want. Okay. Boop, boop. They have the same velocity. And what that means is, because they're in inertial reference frames, they're going to describe the laws of physics the way we usually understand them. Momentum is conserved, energy is conserved. That's what inertial reference frames tell you. But because they're moving at the same speed, because they're moving in the same inertial reference frame, because their velocities are the same, they're going to describe each of the objects having the same velocity, and they're going to describe the same kinetic energy and the same momentum. Okay, let's compare these two people. They're both in inertial reference frames. Let's suppose they're both moving with constant velocities, but the velocities are different. If they're moving in different inertial reference frames, then they're going to come to very different conclusions when they study these boxes. Because they're in inertial reference frames, both are going to say the laws of physics hold, but they're going to disagree on P total. They're going to disagree on how much total momentum there is. They're going to disagree on how much kinetic energy there is. Okay? So, to answer your question, Kamal, your question was very general. You said, if two people are in an inertial reference frame, will they agree on the total momentum and kinetic energy? If two people are in inertial reference frames, they'll both agree on what the laws of physics are. That momentum is conserved. That energy is conserved. But, if they're in different inertial reference frames from each other, if their velocities don't match, then even though they say, yes, momentum is conserved, energy is conserved, they'll both disagree on how much momentum different objects have. They'll both disagree on how much kinetic energy different objects have. Does that make sense? Anyway, that's the answer to your question. All right, last question here. 94. Oh, it's a spring question. A 5 kilogram block suspended from a spring scale is slowly lowered on a vertical spring. What does the scale read before the block touches the vertical spring? If the scale reads 40 newtons when the bottom spring is compressed 30 millimeters, what is K for the bottom spring? How far does the block compress the bottom spring when the scale reads 0? Oh, I love this question. It's about normal forces, y'all. Hold on a second. Okay, so here's the drawing to accompany the question. You got a force gauge. It's a spring. It measures how much force the thing is pulling. 5 kilograms. And then down here, there's another spring. Okay, that we're compressing. So we're lowering. Okay, me name Jeff. I'll add question 3 on page 117 to this list. 117. All right. So essentially what we're going to do is we're going to say acceleration is 0. So net force is equal to 0. But here's the thing. There's two possible forces pushing the 5 kilogram block up. There's gravity pushing it down, and there's two forces pulling it up. I'll call it the scale, F scale, and then there's the normal force from the spring. Call it Fn. Okay? So these three forces are in balance. And we're asking questions where we're given some indication of how strong these forces must be. And then we're asked about the other ones. So, step A. What does the scale read before the block touches the vertical spring? Normal force is a contact force. If it's not in contact, there's no force. So there's only two forces on it. Gravity and F scale. So F scale, it's got to be equal to minus gravity. So this is equal to 5 times 9.81 times that. 49.1 newtons. Pushing up. Question B. If the scale reads 40 newtons when the bottom spring is compressed by 30 meters, hold on. Wait, I don't know what I'm drawing here. Okay, so what we're saying is, what if the spring has been lowered by 0.03 meters, and the scale there's still a scale force, okay? In this case, there are three forces on it. There's Fg, and then there's Fn, and then there's F scale. And because F net is equal to 0, I hat, I hat's in this direction. Okay, because F net's that, it's going to be, they're telling us that the scale reads 40. F net is equal to Fn plus F scale plus Fg. Vector, 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 vector. 0 is equal to the normal force, N, plus the scale force, which is 40, plus gravity, minus 49.1. So N has to equal 9.1 newtons. This is useful because we also know how far it's been compressed. So F spring, force from a spring is K times the displacement. So 9.1 is equal to K times 0.03. So the stiffness of the spring is 303 newtons per meter. Question 3. C. How far does the block compress the bottom spring when the scale reads 0? So when the scale reads 0, there's only two forces on it, Fn and Fg. Okay? And they cancel out. So Fn is equal to plus 49.1 newtons. We know that that's going to be equal to K times the how far it's been squished. So that's 303 times how far it's been squished. So the distance it's been squished is 49.1 divided by 303. 0.16 meter. 16 centimeters. That was a fun question. All right. Boy, I'm really marathoning it. How long have I been at this? 2 hours. Jeepers creepers. You're taking advantage of me. Page 98, question 34. All right. Okay, 34 goes like this. A woman is on a train leaving a station at 4 meters per second while a friend is waving goodbye, runs along the side of the car she's in. If the friend is running at 6 meters per second and moving in the same direction as the train, how fast must the woman walk and in which direction to keep up with him? Once the train has reached a speed of 10 meters per second, how fast must the woman walk and in which direction to keep up with her friend? Okay, so in this question, the friend is a man. I'm going to illustrate what's going on. So here's your dude. And he's running. He's running, trying to keep up with the lady on the train. The train itself is going at 4 meters per second. And there's a lady on the train who is trying to keep up somehow with her friend. So we want them to stay in the same placed relative to one another. It's kind of hard to draw on the side here. Let's draw it from above. The train has a star on it at the front. And here is the woman. And here is Broseph. Okay. So, time to draw some velocities. This person is going 6.0 meters per second. The train is going 4.0 meters per second. In this diagram, how fast does the woman need to go relative to the platform? The woman needs to go 6.0 meters per second relative to the platform. Okay? That's the idea. That's the premise of this question. So here's the thing about the woman is that she doesn't walk relative to the platform. She's not pushing off the platform. She's pushing off the floor of the train. Okay? So, long story short, I showed y'all a method for figuring all this out. I'm going to draw the lady back here. So we need the lady to go like that at 6.0 meters per second. Okay. So obviously we're going to be adding and subtracting vectors here. Which vectors do we add and which vectors do we subtract? The trick to sorting this out is to draw a diagram like this. There are rules of thumb, and maybe you learned them in high school. They're not hard to learn. But I personally have trouble remembering which one to do, and so you should probably do it too. So, how do we keep track of this? The deal here is that there's two reference frames. There's the reference frame of... Okay, hold on. Hold on. There's a dog standing still on the train station. Hello, I'm a dog. Okay. So... when we're listing all these velocities, like that one, and even that one, we're doing so relative to the dog standing still on the platform. All velocities are relative, after all. And so what we want to do is figure out how to convert between different velocities. Okay? How do you do that? Well, essentially, I'm going to draw vectors from the dog to the different moving objects. Forget about this guy. Like, we know that he's moving at 6 meters per second relative to the dog, so the person needs to move at 6 meters per second relative to the dog. We've already taken care of that piece of information. So, actually, you know what? I'm going to maybe I'll take this guy out of the equation. Hey, boyo. Get over here. No! Alright. Good, that's better. So, position relative to the dog of the train. Position relative to the dog of the lady. Position of the lady... whoa, where are you going? Position of the lady relative to the train. These are all vectors, and there is an addition relationship between them. Essentially, here's what I've drawn. This vector, and this vector. And what's the relationship? It's this one plus this one is equal to that one. In other words, x dt, oh, flip off, plus xtl is equal to xdl. The position of the person, the position of the train relative to the dog plus the position of, or rather the front of the train, plus the position of the lady relative to the train is equal to the position of the lady relative to the dog. That makes sense? Okay. So this is just an intermediary. This is just to help us remember how the vectors are added together. You take the derivative of all these. Velocity of the train relative to the dog. Velocity of the lady relative to the train. Velocity of the dog relative to the lady. We know the velocity of the dog relative to the lady is plus 6. We know the velocity of the train relative to the dog is plus 4. So the velocity of the train, of the lady relative to the train is 6 minus 4 plus 2.0 meters per second, which makes a lot of sense. The train is moving forward at 4 meters per second. We want the lady to move forward at 6 meters per second, so the lady inside the train has to move forward at 2 meters per second. Part B. Once the train has reached a speed of 10 meters per second, how fast must the women walk and in which direction? Well, we can rely on essentially what we've sussed out here. We don't need to redo all of this work. What we've just sussed out is the geometric relationship between all these different reference frames, and it still holds true. So in this case, I need the, I still want the velocity of the lady relative to the dog to be 6.0. The velocity of the train relative to the dog is now 10. And so you rearrange this and you get the velocity is 6 minus 10 minus 4.1 meters per second. She has to run backwards at 4 meters per second inside the train to keep up. So first, at the first bit, she's running forward in the train. But then as the train speeds up, she has to run backwards to keep up. Get married already. Oh, who knows? Maybe they are married. It says they're friends, but you never know. Maybe she's shouting out the window, "I'll send you the divorce papers." Okay. Page 117, question 3. Sketch curves to the same scale of kinetic energy versus time for an elastic collision between cart A. Oh, good God. How am I supposed to do that? Okay, hold on, let's think a bit here. Actually, you know what? Let's turn on the graph paper. V. All right. So let's draw the velocity versus time graph for some of these. If they have the same mass, then your initial velocity is going to look like that for A, velocity for B, and then they're going to collide. And after they collide, the relative speed is going to be the same, and so they switch. It looks like that. A, B. All right. I know that usually you draw these as super curvy lines, but the point here is I want it to be easy to see. So the idea is that the total momentum is conserved. It is. The relative velocities the same before and after. It is. Okay. Next one is the two objects. Mass B has twice as much mass. So incidentally, relative velocity is the distance between these two graphs, right? How many questions? Oh, sorry, somebody asked. Martin Lars asks, how many questions are we expected to see, and can you go over an explosive separation question if it's on the exam? Okay, here's the thing. I've been doing this for 2 hours, so unless you have a specific question you want me to do from the book before I quit and finish this question, I'm not gonna do it. But if you can get a question in, I'll do it before the end. All right, it's a time limit. You got to find a good question you want. All right. So, yeah. So it's an elastic collision if the distance between the two lines is the same before and after. All right. So in this one, the second one has twice as much mass as the first one. So so B looks like that at first. And then they collide, and B is going to have let's see, I think A bounces off, goes negative. That wouldn't be the same height though. Should be one apart. Does it look like this? So let's see. Two times 2, 1.5 times 5 times 2. I don't know, looks something like that. And the other one is going to look like this. And they're going to bump into each other. And the other is going to get a lot of momentum. A lot of speed. And this one's going to come up with less speed. It'll look something like that. So from this we can graph the kinetic energy. So the kinetic energy is going to look like half the velocity of each of them squared. So I'll draw it for each of them. So A's kinetic energy looks like this. Maybe like this. It's 4. And then it goes down like that. And B's looks like this. Starts out as 0 and then goes up. In this case, A starts out big and then gets little and then stays kind of little. Whereas A, B starts out small and it gets big. It stays kind of big. And in this case, A, B. This is B. This is A. In this case, A starts out big. And then at this point in time, it decreases. Maybe like that. And B starts out small and then increases. I don't know. Something like that. Maybe I'll make this one go down a little bit lower. Okay. So, hold on. My name, Jeff, asks, is the relationship A1 over A2 is equal to minus M2 over M1? Is that true for all collisions? It's not even true for that collision. You got your M1s and M2s switched. Oh, no, you don't. No, I got it backwards. Okay, so is it true for all collisions? It's true for isolated collisions. When the only force on the objects are from the interaction force, it's always true. So, yeah, it's true for isolated collisions. So, Martin Lars, you're wrong. It's not true for other things. Like, if there's a third cart in there bouncing off stuff, then it's not true. If you put your hand in there and interfere with their collision, it's not true. If they collide when they're going up the hill and gravity's involved, it's not true. It's only true in an isolated system. All right, where was I on this ridiculous question? Yeah, so the deal here is you add them up to get the total. So the total's going to look like this, and it's going to go down to some minimum and then come back up. Total. The total in this case comes down, and then it goes down, and then it comes back up. And the total in this case starts big, and then it goes down, and then it goes back up. What was the point of this? Yeah. I mean, it's asking for a sketch and not like a super good graph. You could do the calculation about exactly how big each of these are. But I think the question it's asking about is like the dip. He wants to see this dip here, but that kind of depends on what the interaction looks like. I don't know, it's not a very good question. I guess it's fine if you're doing stuff, but I don't know. Do you feel like you learned something from it? All right. So now I'm supposed to do page 83, question 57. A two-stage rocket is traveling at 4,000 meters per second before the stages separate. A 3,000 kilogram first stage is pushed away from the second stage with an explosive charge, after which the first stage continues to travel in the same direction at a speed of 2,500 meters per second. 3,000, and it's traveling like this at 4,000 meters per second. And then it blows up. Okay, so it's 3,000 kilogram. Oh no, wait, it's the back one that gets pushed off. So this is the 3,000 kilogram one. And then its velocity afterwards is 2,500 meters per second. So this is 3,000 kilograms, and this part is 1,500 kilograms. This is 1,500 kilograms. Okay. How fast and what direction is the first stage? Is this one traveling? And it's a momentum question. P total is equal to 3,000 times 4,000 plus 1,500 times 4,000 meters per second. All right, so this is MV. 3,000 plus 1,500 times 4,000. So the momentum is 1.8 E67 kilogram meters per second. So after they blow up, the total momentum's still going to be the same because they pushed off each other. So it's mv plus mv. So it's 3,000 times its velocity, 2,500, plus 15,000 times its velocity. Let's calculate what that velocity is. 3,000 times 2,500, 1.8 E7 minus answer divided by 1,500. 7,000 meters per second. So fast. That's pretty fast. How much energy is released by the explosion? Kinetic energy initial. I'm just going to calculate it. I'm tired of writing things out. 4,000 times 4,000 times 3,000 divided by 2 plus 4,000 times 4,000 times 1,500 divided by 2. 3.6 E10 joules. KE final is equal to 7,000 times 7,000 times 1,500 divided by 2 plus 2,500 times 2,500 times 3,000 divided by 2. 4.61 E10 joules. Change in kinetic energy is 1.01 E10 joules. Wow, such a big explosion. Alright, that's it. That's it, I'm done. 2.5 hours with a cold. Better do good on this midterm. I'm done. Have a good night. Go take a bath. Take it easy. I'm sure the midterm will be fine. Stop streaming.